let's see what we have here. Can you guys see this okay? It's a little light. The light's coming on. It's getting a little brighter. Turn them both off. Will you be able to see in here? Over here, can you guys see? Alright. Alright, so we factored this, but we're not able to reduce anything. That's the first step. Well, actually, first you should find your domain restriction. That is after you factor it. So find your domain restriction. We can't use a 4, which makes sense to us. That also is your vertical asymptote. Okay. Horizontal asymptote, go by the chart. When the degree in the numerator is 1 more, do you think it would have had a good rest and would be cooperative? The degree in the numerator is 1 more than the degree in the denominator. That means there's no horizontal asymptote. When we have no horizontal asymptote, check for a slant. A slant says the degree has to be in the numerator 1 more than the degree in the denominator. If it's 2 more, we don't have a slant. But 1 more, we have a slant. So therefore, we have no horizontal, but we have a slant. So we said to find a slant, synthetically divide it. We don't care about the remainder. Remember, when you're going x2, x1, you're going to end up with a line. All your asymptotes are lines so far. So now this comes to y equals x to the 1 plus 7. You can put this in your y2. If you put this in your y1, put this in your y2. The only one you can't put in there is your vertical asymptote, your x equals. But this is nice because you could actually see it guide that. And if you see your slant go up, but you don't actually see the function itself, it's probably because you need to change your window. So you're going to notice in your slants, it's usually going to come in between where you slanted. A slant and a vertical. Or a slant. Well, we'll need that one slant. So now, find your y-intercepts and your x-intercepts algebraically. Make sure you do those algebraically. Max and min, this does have a max, this does have a min. Relative max, relative min. Make sure you give me 3 decimals. Okay. Increasing, decreasing, concavity. Once you find these guys, then go for your range. And then you'll be able to say negative infinity, it stops here. Then I jump over, and it goes again. You can leave these a hard bracket. I left it a soft because we rounded. What the heck? It comes out to y equals x1, but once you do this, our other one that we did in class canceled this out. It canceled out this, so it did become y equals x. But it's a y equals x something line. It's only can be x to the 1. It just so happened that the one we did in class, I think this came out to be a 0. But this one has a 7. So start this at x1, x0. So this becomes y equals x to the 1 plus 7x to the 0. That gives you the plus 7. And concavity, increasing, decreasing. Everybody okay with that? The rest kind of flows the same. These actually are nice for cavities. You see them a little bit better. You see the caves. And again, you may have to adjust your window. This one probably definitely. But once you put the slant line there, it kind of tells you if you're missing something up there. Check your table. Change your window. Questions? You guys okay with this? We're adding one step at a time to these. The rationals work a little bit differently. This one I gave you, right? This was just a regular one. Check your domain first. Factor out the 5. And equal to 0, whatever you want to do. So you can't use a 1. That also is your vertical asymptote. Your horizontal asymptote says the degree in the numerator is less than the degree in the denominator. Therefore, y equals 0 is automatically your, your horizontal asymptote. Draw your asymptotes first and then try to sketch. It cannot cross over a vertical ever. but it can jump over a horizontal. The asymptotes are designed for your end behaviors, to guide those end behaviors. The range, all we take out here is the 0, decreasing, increasing, and concavities. No max, no min. No max or min. Because this technically keeps going up like this. This technically goes down like this. So there's no max here because this point is higher. This point is lower. So there's no max or mins on these. Only when it's a slant, yeah. Don't forget to do your intercepts algebraically. Yep. Once you graph it and you see that this is your asymptote, and you take it out of here, you can see that you're not going to have an x-intercept. And you can see you're only going to have one y. It should all make sense. By the time you do your intercepts, everything should start fitting into place. No increasing, decreasing, because there's no max or min. If you think about it, this keeps going up. So if I said this was my max, this point's higher. This point's higher. Say it again. Oh, this whole thing is decreasing, the whole thing, but not to a point. I thought you meant like to, yeah. Usually these are either going to be increasing or decreasing. If they come this way, or if they go this way, they're decreasing. There's nothing to break them up. Oh, I thought you meant off the max and min. Okay, and last one. This one had a lot to go to it. So we start with your domain. We can factor this guy. 2 perfect squares. We look at your domain. You can't use a -2, so we take it out. That also becomes your vertical asymptote. And we say the degree in the numerator is greater than the degree in the denominator, so we have no horizontal, but we do have a slant. So synthetically divide and get rid of the remainder. And put it in your y2. It's a good way to see, should I have to change my screen here? And I don't think you have to change your screen on this one. Oh, yeah, you do. For this guy. Yeah, you wouldn't see this part down here. But if you see this piece and you see the slant, you know there's got to be another part. This has a relative max, a relative min. It has an increasing, decreasing. It has a concavity. Again, if you want to make these hard brackets, that's fine. Usually we round, so that's fine. God bless you. Concavity. This is a nice concavity. And concave up. Y-intercepts. This had pretty much all of it except for what we're going to do today on here. Can everybody find the slant asymptote? Synthetically divided? Nice, you get rid of the remainder. And put it in your y2. Because if your graph comes over it, then you made a mistake. So you look at it again. A lot of numbers in here. The y-intercept is helpful here, as well as the x. It kind of gives you a little bit more placement for your graph, rather than just whipping it out there. Is to put this in your calculator. I'm going to put it in mine because it's a very strange looking graph. Get it in your calc. Can you get that? numerator was certainly a lot more cooperative. Oops. Okay, so we see a lot going on here. We see something coming this way. We see a little piece over here. We see this piece over here. I'm not really sure where that's going. We're going to have to take a better look at that part in a minute because your calculator really has a hard time when it gets too close to either the x or the y axis. Sometimes it stops and sometimes it draws you a little bit of a thicker line. And something is also going on in here, but I don't know what. So keep this handy. We're not going to sketch it yet, just keep it handy. We're going to have to zoom in a little bit on that guy. So first thing we're going to do is factor in the numerator. I got two minuses, two negatives. So what are factors of 6 that add up to 5? -3, -2. Good. In the denominator, what can I factor out of here? Next. And then what am I going to factor to? I'm going to be x squared minus x minus 6. I'm going to be a plus and minus. -3 plus 2. Everybody good so far? Okay, now, I should be able to reduce this. Before we reduce this, we're going to go do our domain restriction because I need all these pieces in here. So my domain restriction says x cannot be 0, x cannot be -2, x cannot be 3. Agree? I just did something equal to 0. So my domain says negative infinity, jump over -2, start back at -2, stop at the 0, jump over at the 0, go to 3, jump over at the 3, and then to infinity. I have a couple of things that I can't use. And my graph is kind of showing me that. I'm seeing an x of 0. I'm seeing something going on here. I'm seeing an x of -2. I see something going on here. And my x of 3, I'm not really sure because I really can't see that part. So I know something's going on there, but I don't know what yet. So that kind of makes sense to me. So here's my domain restriction. Now, we're going to reduce this side. What factor can I reduce? X minus 3. X minus 3 is going to be our point of discontinuity. Because we're reducing that, I just want you right now to pull over to the side somewhere, say point of discontinuity, and just leave that factor there for a second. Then we're going to rewrite this in factored form. I'm going to leave this over here for a second. So vertical asymptotes. Vertical asymptotes after we factor, that's why we say after we factor, is what's left in our denominator. So x is equal to 0 and x is equal to -2. And that certainly made sense to us, didn't it? So here's my sketch. I've got an x is equal to 0 and I've got an x is equal to -2. I'm leaving my point of discontinuity over there for a minute. Okay, my horizontal asymptote. The horizontal asymptote says if the degree in the numerator is less than the degree in the denominator, then my asymptote is y equals 0. You okay with that? I think it's the first one on the list. So y equals 0 is another asymptote. And we can actually see that this makes sense because there is something going on at the y equals 0 along my x-axis. I can see this kind of go guiding over here. I can see this piece and something's going on over here, but I'm not really sure yet what's going on there. Okay? Now, my point of discontinuity. When I set this equal to 0, my point of discontinuity is at 3. My domain says you can't use 3. but that's just one little point. If I look at my graph, okay, if I look at my graph, I really can't see that I can't use 3. But if I look at my table, I'll be able to see it in here. It'll come down and say, whoops, error. It says -2 error, and I know that. It says 0 error, and it says 3 error. But I can't see why I can't use that. So for now, what we're going to do is we need to get a little bit closer to this. So we know what these look like. We're going to sketch this piece right here. This piece is looking like this. This piece is looking like this somewhere. But I'm not sure where this piece is going. It's kind of just stuck there. So I'm going to zoom in to that part of your screen right now. So we're going to go to your window. And all I care about is from 0 to maybe 4. I'll go to 5. And I want my Y min to be really small, from like -2 to +2. I want to see what's happening on that right-hand side. It says I can't use 3, but I'm not really sure where that's going. So I look to see, and it comes over here. It jumps over here somewhere, and it came up, and then it came over my x-axis and back down. So somewhere it jumped over this axis, and it came back down. I really couldn't tell that, and I can barely still tell that. If you want to get a little bit closer, set your Y to -0.5 and +0.5. Let's see what's happening here. I see it jump over. See it? You got to really narrow in on that screen, otherwise you really can't tell. Now I still can't tell that 3 is open, right? My graph, according to my graph, it looks like it's closed. But according to my table, it says error. This is called the point of discontinuity. There's a little tiny point that's left open. But when you graph this, you cannot tell by your graph because your calculator can't stop at one little tiny increment and actually open it and jump over it. So for us, we're going to take this and we're just going to put a little open circle right here. This is our point of discontinuity. There was a point that it couldn't use. The rest of it looks like it runs real smooth. And we're going to find that point of discontinuity. But your graph, as far as your graph goes, it looks like it's there. Then we did jump over a horizontal axis. This is allowed. But what happens is, if I extend this window, so say I go to 15, you're going to see it come back down a little bit. Watch it come back down. Hopefully it'll come. See it start to come down? It uses the asymptote for end behavior. That's what an asymptote is designed for. To guide the end behaviors. It doesn't matter if it's underneath it or above it. It's still going to come back, and it's going to get real close. It'll never jump over it again. It'll get real close to this axis, but not touch it. So do we see what's going on in this graph? We had to kind of narrow this down a little bit. And how do we know that's there? You can tell by your point of discontinuity something is there. Plus you can kind of tell when your graph just stops short, it's got to go somewhere. So our point of discontinuity should be a point. So I know x is 3. So to find the y, I plug it back into the reduced one. If I plugged it into the original one, it wouldn't work because 3 is my domain restriction, and 3 would set my denominator equal to 0. So I plug it back into this guy to find my y, because it has to be a point. So when I get here, I say y is equal to 3 minus 2 over 3 times 3 plus 2. So this gives me 1 over 15. So my point of discontinuity is this. This is my point of discontinuity. I'll label it A. Okay. All right. That'll help us in a minute after we look for our range and our domain. Now, because this jumps over and comes back down, you have a maximum here. You have a lot going on here. You have a maximum. There's a maximum here, not this guy, and there's a minimum here. And somewhere over here, I'll call this C. Because this went over and came back down, we have a maximum. See this thing when it comes back down? Somewhere up here is a maximum. So we're going to find your maximum. You got a lot going on with this one. But the only thing we don't have in here is a slant. Because if you have a horizontal, you don't have a slant. So let's find your maximum. So your maximum is past our point. So our point was over here. Let's switch these around. Let's go like this and come back down. So your point is here. Your maximum is after your point of discontinuity. So your relative max see if you can find your relative min, just go back to a zoom 6. And find me B, your relative min. Everybody was okay with that one? It means we hit the 3 on the way up. Then we hit a maximum, then we came back down. For this, I set the y's like -1/2 to +1/2. I went from 0 to 15 on the x just so that we could see it actually drop down. You can sometimes tell in your table too. When you come down here, well, it's better to put them in decimal than to keep them in fraction. Then you can kind of see where your y's are going. If they're increasing, decreasing, it's better to go there. Do a zoom 6 and find me this relative min. Anybody find me a relative min? Call it big. Three decimals. So we should have all our pieces now. There's not a lot going on in this graph. And unfortunately, your calculator doesn't do it justice. So you may have to narrow down your windows, you may have to look at your tables, put your tables in decimal rather than fraction. If I get my table, do I just do this? I don't know how to get this to a decimal. I can't get it to a decimal. Anybody know how to get that to a decimal?
You go on the table stack and put it. And this is like a triangle.
Oh yeah, no, it should work. They should come out as decimals rather than fractions.
Just when I type in decimal there.
And then yours come in as decimals, but I don't really want it to increase by a decimal. Well, okay. Thank you. I got this part at least in the decimal. So that you can kind of see what's happening after your 3. See, it went down. It was going down. It's coming up right here. It's still going up to the 4. At the 4, it comes up a little bit more and then starts to come back down. You should see it come back down again. And here we go. We just came back down. So you can see where approximately where it's going to be. We were pretty high up to here, and we came back down. All right. Good? All right, so let's fill in all the other parts. Let's do the x-intercept and the y-intercept. The y-intercept when x is equal to 0 is probably the easier one. So we've got 0, 0, we got a 6 over 0. Do we have a y-intercept? No y-intercept. Does that make sense on your graph? Because your y-axis is an asymptote. So that makes sense. Your x-intercept when y is equal to 0. Oh, sorry, 0 is over the numerator. Use after you factor. So all we have is this guy. We've only got one. That's why before we didn't have to factor, but now we had to factor. So use after you factor. So now we have one intercept. Okay, so what are we missing now? Increasing, decreasing? Watch the increasing, decreasing. This guy over here on the far left is just a complete decreasing part of your function. These are going to have increasing and decreasing because these have max and mins. So this little section here, decreasing. So where are we decreasing from? Negative infinity to where? What's the x value that we stopped at? Negative 2. Okay. Now, we jump up here. We're still decreasing on that part to that min. So we're decreasing from negative 2 to that min value. So take that x, remember their x values. God bless you. Okay, and then we're increasing from here, and we're going to get stopped again at that asymptote. So from here to here, from negative 0.828 to 0, we increase. Just read it left to right instead of try to jump over and do all the increasing, all the decreasing. Just keep going left to right. Yes? Because we do it after we factor. After we factor, this is our reduced one. It's zeros of your numerator. Because if you put this equal to 0, watch, if you put this equal to 0, and you cross multiply that, it wipes it out. Like you could actually put y equals 0, and when you cross multiply this, doesn't it just wipe out whatever was there? So technically it's 0 of your numerator. That's all you have to look at. But we have to factor. We factored one out. That became your point of discontinuity. Before today, we never had to factor. The only time we're factoring is when we get a point of discontinuity. So that's why today it has everything put together. And we jumped an asymptote, we brought it back down, we have max, we have min. This one pretty much has everything your little heart would desire. Good? Okay. So now, we come back here, we're increasing, but we're going to get stuck because we got to jump over the 3. We can't use the 3. So we're increasing from 0 to 3, but we have to jump over the 3. And we still didn't reach our maximum point. So we have to go from 3 to hit your maximum. There's a lot going on in this one. Just follow from left to right with your finger. Okay? So now we increase up to our maximum. Good. Now all we have to do is finish decreasing. And we decrease from our maximum to infinity. It's a lot there. Try not to do all the increasing, decreasing. Just try to read left to right. And like I do, set them both up and then just keep going back and forth. It's easier than trying to find all the decreasing, all the increasing first.
When will you know if there's a point of discontinuity?
When you factor this out and you're able to reduce, that's your point of discontinuity.
So if there's one on the numerator and denominator, they're the same?
Yep, that's a common factor that we can factor out. That's a point of discontinuity. Yes.
There were more than one?
No. For us, it'll only be 1. There could be more than 1, I'm sure, but for us, it's just 1. We can't throw too many things at you. This is probably like the most things you'll see all together. Let's finish your concavity. We have concave up. I don't think we did domain and range either. We did domain. We got to do range. And a concave down. This guy is what? A down. So we were negative infinity to what x value? Negative 2. This is what? Up. Concave up from where to where? To 0. Right? This guy is what? A concave down. A concave down says you still can't use one little point in there. So a concave down, you have to start from 0 and stop where? 3. 3 says error, can't use it. And then continue back from 3 to infinity. This one had a lot. And range. My range says I'm okay here because this guy, even though this stops at the 0, this one goes through it. This one goes through until it hits that point of discontinuity. So it says from negative infinity, when it hits this point of discontinuity, give me that y value. Negative 115. It's positive 115, you're right. Don't know what happens here. Okay, positive 115. Then we're going to jump over that point. We're not going to come back down here. We're going to continue up here to that minimum. And then to infinity. You can take this guy and put it in a decimal if you like. I just left it in a fraction because that's how we did it over there. Either way you want to go with that is fine. It's a lot going on for this one. A lot. Now remember, when you graph these, they're not always going to be as obvious because your calculator kind of stops short. You may have to modify your windows. If you look at your table and you see values out there, but your graph is not going there, change your window just to see what's happening to it. Because otherwise you get stuck and you say, well, that must be done over there. You'll miss your point of discontinuity. And remember, your point of discontinuity does not show up. So if I graph this, and I do this, here's a good way to check this. If I say, what is my value at 3? It's going to say, you don't have a value at 3. So what is my value at 2.99999? You have a value. You have this, 0.06667. If you put this in your calculator 1/15, that's the decimal value. So you can see it approach it. That's a calculus kind of thing. We're approaching, that's a limit. That's what's called the limit. If I actually could fill this point in, and at the end of this course, we revisit this point of discontinuity, and we look at a limit. If I could actually approach this point from the left or from the right, if I could say, what about 3.000001? I'm approaching the same point. What would that point be? It would be this. That's why we call this a point of discontinuity. There's just one little point that it had to jump over. And in calculus, that's the limit we reach. And limits come from both ends. We call this a removable point. And we'll talk about this when we hit this again as we look at your calculus terms. This is removable because from both ends I approach this point. Something that's not removable would be something that goes like this. Something that's not removable is here. It doesn't approach the same point from both ends. But this is called the removable point. Because from both sides, I'm going to hit the same point. And if you put in your calculator, 1 divided by 15, there's that point. See it? It's a good way to check on your calculator to see if you got the whole thing in there. Questions at all? No, this was a big one. Of your range. Okay, so when we went to here, this is the highest point right here at C. We had to add one more point in here. We had to go from 1/15 to this max, 0.086, and then restart at the top. Sorry about that, guys. So make sure we missed that point. Make sure you fill that in.